So thank you, Patrick. And the talk is called Tectonic Growth of North American Cratons and its Associated Basement Mineral Endowment. Right. So thank you, Patrick.
Thank you. So thank you for that nice introduction. Let me tell you a little bit more about how and why I developed this presentation. During a mineral symposium in Socorro, Virgil Luth made a comment that one of the reasons why we have so many minerals in New Mexico and in Arizona is because of the tectonic of the way that we scraped up smokers and the way that we accreted a portion of southern New Mexico and Arizona. And so that kind of got me to thinking, and I decided to do a little more research and came across some relatively new computer programs, simulations, and other items that are only a few years old. And so I worked with those, put together this presentation, and I gave it at about, and Kathy, I don't remember if you were there, but about, now about 16, 18 months ago, I gave it at the Tucson program. And Ed Raines, who was the curator of the museum there at the School of Mines, came up to me. He says, Patrick, he says, this is incredibly new information. Would you mind teaching it to my entire staff and also look at teaching it to the college? And so it was like, well, absolutely. And so I've given it a handful of times now, and it is just, I very much enjoy giving it just because of the fact that it does give me such, it's just, well, I'll get started and then I'll let you guys be the, see that. Let me see if I can pull up where's the little pointer? Well, let me keep going. So as was talked about, the tectonic growth North America Craton, that's a first part of the discussion. The second part of the discussion will be these basement mineral endowments, because you have to have the minerals in the basement, and so the endowment, and you have to have a method in which to get them out of the mantle and out of the basement rock in order to have them come to the crust where we can actually utilize them. So with that, with again, the general idea of accretion, we'll look at it from pre-Cambrian up until about the beginning of Cambrian. And then the last part of it is we're going to look at some new information on our basement mineral endowment. To get started, I want to go over some terms and I want to go over some concepts that'll make the rest of it go a lot smoother and just kind of make you aware of what's going on. And a lot of you, if you know this, then I apologize, but it's important to kind of understand it from the beginning. The whole reason why we have plate tectonics has to do with the fact that we have the upper section, which is the obviously the continental craton areas, or we have the crust area. Below that, we have the lithosphere that makes up the mantle, and then it goes down to about 70 kilometers thereabout. And then you have the asthenosphere. The asthenosphere goes down quite a bit. It actually goes down to almost 3,000 kilometers. This is hard, very, very hard, cold, rigid, which is one of the reasons why you have the plates that move, and you don't have it's not like a lot of jello that you're moving across. And then the asthenosphere, though, is hot and plastic. So as the heat comes off of the core and rises up, it actually comes up and starts circulating as it heats up. And then as it releases its heat, then it sinks back down. As it does that, it drags the crust along its way and along these different little boundaries. The other concept to understand is when you look at plate tectonics, and this is in particular related to ocean crust and continental crust and kind of what happens. And we're going to talk about this a lot. So I want to spend just a couple of discussions on it. We get this rising decompressed matrix parent, and it's really kind of an ultra matrix. And I'll go over what matrix looks like and why it does this, and the density as it rises up from the heat, as it comes up and it pushes the plate as it comes down. As the plate comes down and heats up, when it hits the continental plate, it sets up this accretionary wedge. This is material that is sedimentary material that has fallen off the continent and has come down and has fallen down onto this oceanic crust. And as it goes by, it just basically scrapes it up and moves it. And this will be important in just a few minutes. The other important part to understand is as this mafic material, very heavy, very dense, as it gets down and heats up, it starts to melt. Then it becomes more felsic, and the felsic, as it is, has a less gravity. The specific bulk gravity is less. It starts to bubble up, and this granite I'm going to show you becomes very important for cementing some of these different continental items together. So we start with mafic. It comes down. As it melts, it becomes more felsic, and it rises up because of the differences in the density. To put it in another way, this is granite. It's very felsic. It has a high silica, 70%. This granite here is also equivalent to what we would look at as rhyolite if it actually comes up to the surface. And so this is very, very felsic. It's also gets more onto the acid side. On the other hand, the ultramafic, you're looking at a lot more manganese oxides. You have very little silica. You've got 40% silica versus 70%. And then you've got 48% versus 0.1% or 1% over here in the magnesium oxide. From a density perspective, the rhyolite or a mafic type granite has a bulk density of about 2.49. And I'm not expecting anyone to memorize or deal with any of this. But as you get more and more onto the mafic side from the felsic side and get over to the so if you start looking at this, some of the ultra mafics, you're talking about 2.95, 3 grams per cc. That's about 20% more dense than the rhyolite. So you can kind of see why it rises, because if all your rock that's in the main portion of the mantle is going to be more of your ultramafic, if you start to get some of your, as it turns felsic, then the density goes to lighter and lighter, and it rises up to the top. So pretty basic, but it plays an incredibly important role. Basic physics plays an incredible role on everything that we're going to be talking about here. We're going to talk a lot about different arcs. We're talking about volcanic arcs. This is a oceanic to continental convergence. This is what you'll see. We had the folks from up there in Oregon, Washington. This is exactly what we're seeing. We got an oceanic crust. We've got some of the lithosphere that's going down with it. As it goes down, it comes down, it melts, and it comes up. The crushing, or this accretionary wedge right here, pushes pressure and causes this volcanic arch here with a trench that's right up along the lines. And we're going to go into that even in more details because it also plays an important role. Here's a continental to continental crust, is where it's, again, very heavy. One of them is going to start moving down, start going up underneath it, starts going down to the asthenosphere, but it's going to cause a huge mountains, and we'll look at examples of those. And then the last one is where you have oceanic crust hitting oceanic crust, and it sets up a series of island arcs that are off the ground, and then it also sets up this item. Some of the other terms I'll be using is a back arc basin. A back arc basin, and I'll show it to you in a diagram, is where it's a spreading center. So as this material is moving this way, this material is moving this way, and so it's a spreading center. We've got a convergent boundary where we come down, and again, here's this accretionary wedge. and it comes down subduction zone, continental crate. We have continental margin, the ocean basin. This is also another divergent plate boundary that is where you have the back arc. This is also the same thing, comes up and it pushes it both directions, and volcanic arc, microcontinent. But this is going to be the key to understanding the accretionary processes that occurred in about the last 500 million years or so of the Cambrian period. This is called the Banda Arc. It's in Indonesia. This is what we use, and by looking at the geology all over Canada, all the ways down into New Mexico, all the ways over onto the East Coast, and understanding what happened with your Appalachians, this is the key to understand what's going on. What we have is we have a Australian continental crust. It's contacted the Banda Sea plate, and it's also, there's a third plate up here, is the Southeastern Asian plate. So you actually have three plates that are coming into contact to each other, but it gives you an idea. Here we're talking about ranges of somewhere in the neighborhood of 600 to 800 kilometers. What we saw on the southern side of Laurentia, we saw zones that were 1,500 to 2,000 kilometers in length, and we think that they were set up exactly like that. Here's what's happening. The Australian crust has come over. It started to go up underneath the oceanic crust. As it started to decay, here's now what it's done is it's created this mountain zones. And so the first portions to be scraped up is the sedimentary rock that was on top of the ocean crust, because it's up there on top, but then it's going to be picked up first and it gets packed up. The next one is the next set of what, as you read up here, the Triassic and Jurassic zones. So you get into this series of belts, and these are arcs. So if you look at these in details, this rock goes up and around, up and around, and up and around. So now all of a sudden, when you start trying to understand everything, what's going on, and realizing that you're going from younger to deeper, older as you're going through. And finally, this last one is metamorphosized basement rocks. And then as this starts to come down, scrapes all these up, it sets up this mountain range, and it sets up this trough. This trough here just has to do with the mountain, and then it comes back up. It's like you take a rug and you shove it on the backside, you're going to get an area that's going to dip down. So this is called a trough here. This is a back arch. So what's happening is this is all under compression. This is no longer under compression, and it's actually spreading. Then you have a series of volcanic islands that form it. So here you can see it. The first arc, the oceanic crust, you then start to see, or the sedimentation, you start to see the older rock, you still see the even more rock. You now start to see the back arc, where it just is spreading. And then you get these huge volcanic islands going across here. And so you're looking at 200 to 300 kilometers across here. You're looking at 600 to 800 kilometers across here. But, and again, we'll go through this in a little more, but if you understand that we're picking up sedimentary rock, we're picking up other rocks that's underneath, then that'll help you understand the next portions of it. So, and then what happens is on this one here, we're kind of showing multiple plates as they're moving. And this is what I was talking about related to the granite. As we started with some hot spots, Hawaii is a hot spot, for example. As this plate moves on, then you get more and more islands that tie together, hot spots that join together. And then as this plate submerges, then you get the mafic, you get the rock that melts. It comes up, it turns more felsic, and it gives you a large granite plume that sutures all these together. So that's why I was telling you that the granite is very important and how it comes up, because you're going to see this happens time and time again, islands, arcs, and then you're going to see the last phase is this granite cementation of all this parent material. So with that, let's get started into the fun stuff. Now that you guys have the basics and you're smart on all the different terminology. This is Nishoshima. It's off of the coast of Japan. It first came up. It's a hot spot. When it first rose up in 2013, it was a little less than a kilometer across. Here a few years ago, when they went back and took a look at it, it's actually over 13 kilometers now in size. So it's 13 times the size that it originally was, only over a period of about 10 years. It is a hot spot similar to like Hawaii. We were talking a little bit about what's happening in Hawaii, so this is a stationary hot spot that comes up. It breaks through the lithosphere. It creates all these little islands that come up as it builds up this different volcanic, primarily mafic type rock, which is the black stuff that you see. And by the way, the mafic is, because of the low water content, is the reason why the mafic rock just kind of comes out and pours, comes out vents, it just kind of pours. It doesn't explode like some of the other ones that have a lot of water and have a lot of silica to it. So this is what's happened is this was a hot spot, and as this direction of the plate has moved, it was originally here on Kauai. As the plate moved, it then made Molokai, and now it's on the big island of Hawaii. This is what we expected to kind of occur quite often. And let me go through now real quick of some of the examples. The ocean to ocean type that we'll again talk quite a bit about is the Aleutian Islands. This is the Aleutian Islands off of Alaska. And so what you have here is this is oceanic plate here. You have a larger plate here behind it that's kind of pushing it up. And as this goes up, well, then you're getting these islands as it's being subducted under this other oceanic plate. You're getting a whole series of islands. And if you know about these islands, this chain here is several thousand miles in length. So these can be very, very, very large features. The Himalayan mountains are an example of the continental to continental plate. And this is going to be important when we start talking about eastern coast and what happened in your mountains in the Adirondack, and that was actually that was very similar to this, and it was a continental plate collision with a continental plate. And then we'll also talk quite a bit about what's happening in the Mount St. Helens and in the Pacific Northwest, where you have these different mid-ocean ridges comes in, and it's actually formed. You got a subduction zone, and it's melted, created the Cascade Mountains. You also have the Olympic Mountains that have been formed as a result of remember I said that the accretionary wedge can get to be pretty large. Well, if you know the Olympic Mountains, you know that they are quite large. But the Puget Sound is also a trough. So you've got this that's pulled up here. It has lowered this zone and created this trough, which now is filled with ocean water and the Puget Sound, Cascade Mountains, and then you have the North American plate. So now the fun part comes in. I'm going to go through this relatively quick. This is the Canadian Shield, and this is based off of some high-speed computer modeling that's only was done just a few years ago. This is about 2 billion years ago. Prior to 2 billion years ago, in fact, the first sign of water appears to have occurred of about 4 billion years ago, where you figure that most of the Earth is about 4.5 as far as rocks, 4.5 billion, to where everything kind of came together. So it had 2 billion years to where you had hot spots and other smaller continentals to form. These are referred to as microcontinents. You have the superior continents. You have 12 different these microcontinents. And what you're going to see is the slave. This one has been held to where the Ray province has been held in its place. You're going to see that the slave, and because the way that we did this was all dated. looked at zircons in between these, and by dating it, we know the relatively age of when everything came together. You're going to see the Slave Province come together, and because these are continental plates, even if they're microcontinents, then this is going to be continental to continental subduction and running things together. So you're going to see very, very large mountains. You're going to see the Nang province come down. You're going to see this province come over and join, Superior come up, Wyoming, Medicine Hat come together, Sac move up. And so we're going to go through that relatively quickly. You get some arcs because now that the Slave has come down, it has, this is, in this case was originally oceanic crust coming under continental, but it set up this great big trough or this arc zone in that section there. It's now extended out, but now the Name province and these provinces have come together. We moved the Superior up. This mountain building based off of the Bear Arc is now starting to grow. It comes together and it forms the Trans-Hudson. This is a very, very large zone, which at the origin here, these mountains originally were the size of the Himalayas. And you can see how it's being subducted on this side and being subducted on that side. And it has just caused a huge, huge mountain range to come up through it. And we know that it actually extended all the ways up. We got the New Quebec subduction of the zone as well. And we got the Fox Belt, and the Wyoming is starting to come up. Mojave has not yet quite done too much stuff. And the last portion of it is when you get the Wyoming province comes up, Medicine Hat joins, and then we start to get a little arc zone in here. So this is the first 200 million years that our continental plate came together. This is what we looked like, and it's still considered to be very stable. But what I also want you guys to notice, because it'll play the role in the next portion of, is you see that this Trans-Hudson, this origin has been truncated off, and I'll explain about what happened there. The next 500 million years, how the continent grew is now the process is going to change dramatically. And that's why I wanted you to understand the arc and understand what was happening down there. So the first thing that started to happen is we started to get some subduction here, and we started to form up here in Colorado, New Mexico. These are juvenile arcs, and they were exactly this. They were oceanic to oceanic with the continental crust, and you got this island chain. So this is the arcs that we're talking about here, and you can see that they extend quite extensively. That grows, and you have this, all of a sudden you have this huge, what's the Yavapai province, and again, it's being subducted, and you can see that this extends all the ways up from Michigan, all the ways down into Arizona and Southern California. The other part that's happened is because of subduction, the Mojave plate has now joined in and is now part of our continental plate. So these are now all kinds of individual arcs. And then you have a suture line that goes up along there. Remember I talked about the granite? So we've accreted all this zone that tends to have a lot of juvenile crust on it. It's mafics, it's smokers, it's volcanoes, and it now gets cemented together with all kinds of granitoids that cement this Yavapai and make it into a new section. But now we're starting to look at a new subduction zone below that, and we start looking at the Manzano. So this is the Yavapai province that's very highly well known. We then go in, this is what we think it looked like. So this is from the deep map. This is about 1.7 billion years ago. You have the Yavapai province, you have the subduction zones, and so you have all this juvenile, you got these arcs that go in, arcs on the outside. You start to get the Matsuzal province is starting to look at possibly be forming. And so this is what we look like when all of a sudden all the mountains start coming out. Tremendous mountains along the edges and also along the different arcs. and we start to get the muscles. And the muscle will come into our province exactly the same way. These were island arcs that have joined together, but now the Matsuzal goes all the ways up into the Hudson zone and goes up along, you can see Maine, you can see the other northeast, your folks part of it, the Labradorian type province. So this is a huge type of subduction zone, and you have all these little arcs that go along that entire zone. It's also juvenile crust. It tends to be island arcs. You start to get a few more, you start to get some of the granite starts to cement some of this lower section, and you start to get a little bit more of the granite intrusions. And then about the same time, we get what's referred to as the granite rhyolite. And this province here, by the way, if you know anything about New Mexico and the Jemez Landerman, and you know about the calderas that's just north of us, that caldera zone is right in here. And it's where this zone came down through between the Matsuzal zone, and it's where it makes a turn. And it's also where the crustal extension from the Rio Grande Rift, it's where they intersect. That's one reason why we had such a weak spot there, the explosions of the items. But you had very similar items of what was going on here. Again, subduction in this zone, subduction in this area here, but you had huge amounts of rhyolites. You have it all the ways over into West Texas. You had it in New Mexico. You had it some of the areas. I had some people ask me as well, did we ever have large calderas in Oklahoma or anywhere in the South? The answer is yes, but they're in our lower zones and provinces. And so the only ones that we've ever been able to really identify with any kind of certainty are the ones in Texas, New Mexico, and some of the Arizona. So the granite would come later. So this is the rhyolite portion of this province zones. There's the granite. Look at the amount of granite. This granite, we think that the heat came from part of it from the zone up here, and also what was happening, but we also think because of the compression that it just formed all this huge amounts of heat from all this volcanic activities that helped form this rhyolite. All this heat and the thickening of the crust caused all this granite to be formed, and this granite came up and cemented this entire section together. Now we start to impact more on the upper East Coast, the Grenville. You guys, I imagine just about everyone up there has heard about the Grenville activity. This was actually at 1.3 to 1.1. This was the makeup of the supercontinent Rodinia. And so if you look at this, this is our East Coast zone, and you start looking at the compression of what was happening, then you ended up with a large compression zone. And at about 1 billion years is where you also got where they think that we actually hit a South American, that actually Amazonian plate that helped create all this collision. So this was a mountain range. This was a continental to continental mountain range zone that we believe was as high as the Himalayas are now. But as you know, they've been highly eroded down. But think about that you had a Himalayans right back behind in your backyard. We then also have granite that comes in and starts cementing some of the provinces together. You got granite that excludes out and is actually being projected in all the ways down into Colorado and down into southern Texas. So this is actually a large granite boulder field, granitoid field. And we don't know exactly what happens here, but we think that it actually helped thicken the crust and help cement together this rhyolite granite zone here. We then start some rifts, mid-continent rifts, Fort Wayne rifts. We start to get in rifts up here. This is the Mackenzie Dikes. This is a rift zones and dikes. You also have here, up here, and the next phase of that rifting is off of the west coast of Laurentia. This is the rifting belt. You also have some supergroups, some granite that's also being included in, and this entire section is now rifting, it's pulling away. This is about where we get into the breakup of the continent of the of Rodinia. And so we think that part of this, because of the breakup of it, that this block, as it pulled apart, set up these kind of rift valleys and rift sections. That rift continues, and it continues along the eastern ridge, eastern margin of Laurentia. And then at the end of the Paleozoic period, then it's pretty much what we see today, only this time this Precordalia has broken off. It broke off of Texas, Oklahoma. And what this is, what they call this is a Spanish word that means mountains before mountains. So what this was a series of mountains, and this actually transitioned down. We weren't that far away from South America, and this block is now found in Argentina, and we've matched it up to the geology of what we've had here. So this is forms the core of our continental plate. Let's look very quickly at the eastern and western margin. Let's look at your section. 400 million years ago, you started to have, again, some of the island arc. You're starting to accrete some of the island arcs. You have the tectonic terrains. You have the New York Bight area, Western Ocean. So now you've got oceanic to oceanic. You got the island arcs. It moves in, it hits, and another one's right behind it. You set up some accretionary wedge. It starts to really deform some of the zones as the continental plate starts to move in. And then during the Permian period, you had the formation of the supercontinent of Pangaea came in. So you had North Africa, parts of Europe came up and actually pushed everything together. And these are all accretionary wedges that have been covered up now with sedimentary rock, but we still have movement of the continental plates moving together. And then eventually when it at 250 million years, then you got this basin, and this basin tend to deepen. On the west coast side of it, I'll go through this. What you're looking at here is these are the different plates. This is the Farallon plate. This is the zones of where it's at. And so what you're looking at here is this is a map of how it's being, the Farallon plate. It comes down, and all of a sudden you're starting to look at all these accretions zones that actually help form the west coast of North America. What I want you to notice is that you have some really strange, we know that the Farallon plate was not just one plate. We know that the Farallon plate was at least 5 different plates. We know that because we can take a look at the parent material of the rocks that make up, because of the accretionary wedges that make up in everywhere from Nevada to California, all the ways down into Arizona. Some of them are extremely exotic, and as we don't know where they came from, but they were certainly not generated right next to the coast of North America. We then have, so this is as it been a little bit farther, now it starts to move a little bit farther inland, Farallon plate starts subducting under the main continental plate. You get more of these subduction, these accretionary wedges build up even more, to where you then look at 75 million years ago, the Farallon plate is now all the ways underneath central United States, and you're now getting all the accretionary wedges. You're getting some very exotic, and you're getting some very strange plates and different materials. By 55 million years, and almost today, we think that the Farallon plate is just about to reach the east coast of the United States, and it actually goes down, and this gives you the depths. So you can see that the Farallon plate is diving down. You can see that on the leading edge, you're talking about 1,400 kilometers, and the outside edge 600 kilometers. So it's diving down up underneath. And now pretty much the accretionary, everything is pretty well done. We now have, about this time is when we transition, actually about another 20 million years from now, we'll transition from this plate to a lateral, which is where you have the, for all practical purpose, the United States plate going south. You've got the Pacific plate headed up toward the north. That also, and what we ended up with, to kind of look at tying everything together, we talked about all the Canadian shield zones. We talked about the Wyoming plate. So that's why you start talking about dates of 2.4 billion to 3.6 billion. You got a portion of the Superior plate over here. You've got some of the wedges that come through in here. You now have in this zone here, you've got the Yavapai, you got the Matzal, you have the crust related to the granitoid, and you also have the rhyolite zone in here. Now you start to see a lot of these accretionary zones where you had all this island arcs along this zone, and you also had the continental collisions, and it goes all the ways up into Alaska. You see a very similar zone. And what the, I'll call it, I'm not going to call it the final results, but I'm going to call it the kind of why it becomes so important to understand your basement rock. If you're really going to understand and look at the minerals, this is a plot from USGS based off of the basement rock of all the mines, major mines and mining districts in the United States. And it's overlaid on it. And you can see where this is the Rio Grande Rift zones, primarily that forms here. You get down here, you start to get into there's some of the other plates where we've picked up a lot of smokers. Also here, we've picked up a lot of smokers in the accretionary of the Matzal plate. But now start taking a look at what's going on here in Nevada, and you start looking at all these zones in here where you start talking about this yellow zone that's about 40 million years. You've got the shoe fly zone that's up in this area here, but you start looking at it, all the reds is the gold and silver. We've got lots, you've got the orange is copper. So this is where we picked up a lot of different smokers. Colorado, because of the mineral belt, you actually have the Colorado mineral belt limonite goes right through here. So this is the Colorado mineral belt. This section here, you do have, because of the Rocky Mountains and some of the volcanic activities, you have it coming up here through Montana, Idaho, and going all the ways up into this area. But this is what I mean by saying, so you have to have two items to really have minerals that are at the surface that are, I'll call it these precious metals. You've got to have one, you got to have it in the basement rock. And then you have to have a way in which to bring it from the mantle or from the lower portion of our upper zone of our lithosphere and our crust to bring it up to the surface. So you start mapping this against volcanic activities, lots and lots. This is the area of San Juan, the Bachelor caldera is right. This is the Crete area. One of the largest calderas ever exploded in the world is right in this zone here. Lots of silver, lots of gold mined in that area. We had lots in New Mexico here, calderas throughout this area in about 30 million years ago, because in about the last 30 million years after the Farallon plate subducted in on the left side, we've been in crustal extension through that entire period. As you get the crustal extension, you open up blocks, and this is the manifestation of some of the original is all these calderas in this area, also down in southern Arizona, and then all the ways up in Nevada. This just has to do with a lot of volcanic activities. Death Valley, let's see, right over in here, you get a lot of zone, one of the lowest, that's a crustal extension zone, lowest point in the United States. And then you get here within the shoe fly formation. This has to do primarily with not a whole lot of volcanics, but some very, very shallow, very, very unique and very, very special accretionary material that has actually been brought up here. And you can see that it extends all the ways back up into this zone. The sources that make up the primarily ones, the tectonic model that you saw is from the Whitmire and Kallstrom. Is the growth on it. It's 2007. You start looking at the map of the basement domain. It's 2015. Also the mid-oceanic and some of the other subduction zone, 2013. And I use some actual new material that actually goes back only as far as about 2019. So with that, that kind of concludes it. Let me see if there's any. No, these are just general backup. So with that, I will take any questions. Let me go ahead and let me stop sharing.
Well, thank you, Patrick. Oh my goodness. So much to absorb. And
It is.
Stare at that mining map for a long time. That is something else.
And that's what got Ed Raines from up there, because it's one of the few. And like I said, I had to pull it together. They didn't pull it together to show everything. But Ed Raines came to the same conclusion I did of, oh my goodness, this all now makes sense of not only why we have the caldera activities because of the crustal extension, but also because of showing how we ended up with all this basement domain minerals and why there's central United States. There's a little bit of lead and zinc. You got Illinois where you got some of the fluorites, and you've got some of the items. You've got a little bit of gold here. In fact, some of the first gold that was ever discovered here, South Carolina, down in this area here. But there's just not a whole lot of material. And a lot of it has to do because of the exotic accretion we had here and because of what was happening within this bed zone. Dave, you have a question? I know you're just dying to ask me a question.
I was just wondering, is you talked about the number of plates, the different plates off the West Coast during the, I think it was Upper Jurassic, Cretaceous, that
Yep.
the Farallon plate was 4 or 5 plates.
Yes, sir.
So that means that those plates were that there were ridges between
Yes, sir.
those plates.
Yes, sir.
What happens when you subduct a ridge?
Normally what happens is it gets accreted onto the continental zone. It scrapes it up off.
The whole but doesn't the ridge continue? Doesn't that plate geometry continue to extend when you're subducting it in the subduction geometry?
It tends to actually just build up and it tends to fold. That's why I showed you the showing you the accretionary wedges of what was happening down there in between Australia and the areas. Is those ridges for the most part end up being pushed up against. If you have, for example, in this case where you had the Cascade Mountains that were right up on the edge because of the oceanic to oceanic, well then now all of a sudden you get pushed up. You sometimes will have a basin in between, but then you'll get this other set of accretionary mountains that will actually form. And because of the accretionary mountains, because of the way that they're compacted against the other mountains, and because of the compression, you end up getting a tremendous amount of heat, and the complexity of what you can end up with. In fact, what you see in Northern California, the complexity of from the metamorphic all the ways to the accretionary plates and the rollovers and of all this material, it is incredibly complicated.
I know. Yeah. Yeah.
So, that's what it tends to do, Dave, is it tends to scrape it up because you're actually scraping all the ways down to inside the oceanic crust. And so you're actually pulling stuff off of even within that zone. And we think that it can be up to 1 kilometer or more into that zone.
Wow.
Yeah. So you can really get some weird things, but you're absolutely right. We ended up with hot spots. We ended up with other items that went in between the plates. And it's because of what we're doing on the modeling that we're understanding that the Farallon plate may have been more. We know that it's at least 5 different plates, may have been even more than that.
Wow.
Andy, I can see a question on your lips, buddy.
Yeah, you're a good teacher, Patrick. You saw all the question marks. I don't pretend to understand this, but you use the term complexity, tremendous complexity.
Yes.
Are you describing there a diversity of minerals? Are you describing a confusion, a spaghetti of different kinds of plate after effects? Can you tell us more about what this complexity is, or the super complexity?
Let me look to see if I can find a report and I'll share it with you. This report is, like I said, pretty new, and it gives you give me just a second. But to answer your question directly, it's because of these different accretionary wedges and because of the compression and the metamorphic that alters the different rocks. So you've got a mountain range that's already been crunched up, and the geology, you got different layers upon layers. And now you're taking material from the ocean and you're accreting it and you're folding it and you're making multiple folds. So spaghetti would be a good term for you to use. But you have another one just behind it that's older rock. And so you get these complexes, swirls and complexities on there that are just absolutely, I think it's just absolutely gorgeous. But it can be incredibly complicated from a physical geology perspective, and just makes it to where it's like, wow. Let me see, give me just a second. And I want to see if I can. Okay, I'm going to reshare my screen. Can you see that all right?
Nothing.
Oh, nothing? How about now?
You've got a black screen, so the space. Okay, now it has showed up. Yes.
Okay, so I'm going to take, this is, well, let me take you down to a different one. This one shows, okay, this is the geologic map of Northern California, Southern Oregon. Each one of these sections is a different, yeah.
Yeah.
You see what, now you understand,
Yes.
Andy, what I was saying? So, and a lot of these belts are belts that actually came up and folded over and overlapping each other. So you're looking at 2 sides. You could be looking at the same sides of a fold, or be looking at an underside of a fold, depending on how the erosion brought it out. So if you start looking at, again, all these different zones, but yeah, I think your term spaghetti, and I think a lot of meatballs and a lot of meat sauce and trying to separate it off I think your term is wonderful, Andy. I love it. Spaghetti.
Okay. Thank you.
Did you like that one, Dave? I think that one kind of
Yeah.
answered your question as well.
A little bit, yeah. Have you done any research, or do you want to weigh in on this whole idea of the northward translation of some of the rocks, the whole Baja BC concept I've been doing some reading about, and sort of has been been talked about for the last 40 or 50 years, that the paleomag suggests that many of the rocks in Oregon, Northern California, Alaska came from way, way south. What does that influence your mineral exploration and mineral emplacement in any way?
This is what we're kind of thinking as well, is when the research that I've done also shows that that the translation of some of the material, that when Rodinia broke off, that some of the material that was left behind looks like, and the way it's moved within the zone may have indeed been from saying that mine's unstable, so you guys may be seeing a delay in the items, is I believe that they are correct, that the lateral transition and what we have. And the other thing I wanted to say, and I forgot to say it at the time, is when the Hudson transition, and I made the comment that said, hey, this was truncated at the Matzazal zone. Remember that image where you saw the Hudson come down and they get truncated? What we're now also thinking, and it's not necessarily alternative, but it fits in with what we're seeing on some of the Yavapai geology, is that some of that material from the Hudson got intermixed with the island arcs of the Yavapai zone. And so you actually had in some zones continental to continental, or continental to arc, and then arc to continent collisions. And so that's one reason why in that southern Arizona portion of it, we actually think that may have happened quite a bit, and that a lot of that rich rock from the Hudson zone may have ended up down there that helped make up some of the smokers in the continental and continental collisions that happened in the lower section of the Yavapai zone. So bottom line is we've learned a lot, but I think that I'm very excited for the kids and what they're finding out, what they're doing. They have access to instrumentation that, Dave, you and I just dreamed about when we were in college and we were dealing within the zones. But I do believe that a lot of that zone, that there was a lot more break-offs and movement of material than we have any idea or can really. I mean, who would think that we would break off a portion of Texas and Oklahoma and it would end up in Argentina?
Yeah, really.
Hey, Patrick, I have a question more from a current applied side situation. Do you think any of these studies in terms amongst the oil and natural gas geology industry is impacting the way that they're viewing current day oil and natural gas exploration in light of this data?
I don't know, Robert. When I was in college, I was related into the oil and gas, and we were interested in a lot of these items. My personal opinion is no, and the reason for it is what they're looking for is primarily you're looking at either zones that oil and gas was disposed of in the Pennsylvania, Mississippian age during those where we also get our coal, or out here in the West, primarily the Cretaceous zones. And you start looking at some of the Cretaceous zones and where you had the large amount of biomass that would help make the oil and gas as well as the material. You don't find it within these zones, and you don't tend to find it in the accretionary zones. If you do, it's like you find down at Burbank, you find that some of those areas, it's very, very complicated to determine it. And what you really do is follow a specific accretionary zone and look for it in that specific. And you can get 10 feet away and you're in a fault zone and you're going to find nothing.
So it's not going to affect something, say, exploration in the Permian Basin, something along that
I
order?
don't think so, because almost all that is sedimentary. You're talking
Okay.
about oil and gas that's trapped underneath the limestone. And so, well, I think the one part that it will help out is that the oil and gas business is pumping a lot of money into supercomputers and kids and other parts that are learning so that they can keep up with the technology. But I don't think it's going to change that much on the exploration of what's happening, at least in North America.
Thanks.
So, yeah, Andy, I don't see any more questions on your lip, but I'm starting to see one on Ken's. Come
Now,
on,
would that
guys,
be Ken
hit me.
Rock or Kenny Reynolds?
You, my friend.
Ken on screen. Did you
Well,
have-
that was an excellent presentation, Patrick. As always, you just blow us away. I wish I could even begin to understand all this, but thank goodness there's people like you to figure it out for us.
Well, I appreciate that, but you can also see why I went beyond just the basement rocks, and it was the timing was perfect for USGS to overlay their mining district map, because now it brought it together. And I think you would probably feel the same way. It's nice to understand how we got to our plate, how it came together, but to understand the consequences of how it relates to our mining district and our minerals, to me, is like the icing on the top of the cake.
I agree. It's wonderful. So, any other questions for Patrick?
I think we're going to have to go away and think about this and come back.
Yeah.
It's a lot to absorb.
It is, Andy. That's why I spent so much time up front, because if you understand the general concepts on the items, and if you want me to take a couple minutes and go back to any of that, but that island that I showed you of what's happening down off of the Australian in northern Australia, that is the key to understanding how the lower portion of the United States, of the US continent, came together. The Canadian Shield, think about it as a bunch of microcontinents that joined together. These microcontinents were formed in the first 200 billion years. And that when we started out 400 billion years ago, there was probably very few to no islands. The earth was covered with water. There may have been islands underneath the sea. Then we started having hot spots. The hot spots went together. They formed, they got cemented together with granite. Those zones then grew and grew. And then at 2 billion years ago, we were in the zone to now start to build the Canadian Shield, where prior to 2 billion years, we were not in a position to build the Canadian Shield.
I just think it's very interesting that I live on the accreted terrain called Silesia, and I'm on the slow boat to from Oregon all the way up to Alaska.
Yes, ma'am. Like I was telling some friends, it's, I said, LA is really not part of this continent. It really is part of the Pacific plate. And in about 40,000 years, when it becomes a suburb of San Francisco, we'll all wave.
Yeah.
I have a
To
question,
think that all
Patrick.
that land,
Hi,
moved-
Kathy.
that Baja BC moved all the way 3,000 kilometers.
Yes, ma'am. Amazing, isn't it?
So Patrick, I loved your presentation. It's hard to wrap my head around what you're doing, but how are cratons formed?
This is actually, if you look at it as this is exactly how they're formed, is through this process. A craton is, for example, a microcontinent or craton is, for the most part, in fact, even Europe and most of the other ones formed exactly the way our craton and how our unit was actually formed. And it starts with microcontinents. And then the microcontinents are little cratons. And then those cratons grow into larger to continental size. And then you end up with these different larger platforms. And then you get all kinds of wonderful things that happen in the interior, like the Colorado Plateau and how it's impacted and how it was helped form and how it's a super thick zone. And what a lot of people don't know is that the Colorado Plateau rotated about 15 degrees from where it's at today.
Hmm.
How did that affect everything around us?
Thank you.
So again, bottom line, time. Little bit here, little bit there, and over 2 billion years, a little bit here and a little bit there becomes a lot.
Mhm.